Thanks so much. It's a great pleasure to be here. So the physics part is going to be a bunch of comments about recent work with many collaborators, including Nari and his student, and also some upcoming work. But first I would like to start with a little bit of comments. I've known Nari for almost 8 years, so I just have a few small comments to make. So there is this famous quote that Nari said that space and time are illusions and they would be replaced by something more sophisticated and more interesting. And one of the first things that I learned from my own experience is that I would send some primitive idea, like some sketch of something, to Nari, and he would always manage to somehow somehow extract the most interesting and sophisticated part from that story, make it much more interesting. And then I think he has a real knack for this kind of thing, of finding the key point in arguments or find the key points in some ideas and capitalizing on that. The other thing is that when I just arrived at the IIS, Nari somehow asked me lots of questions. And it started from very, very easy questions. Like on my very first day when I first met him, he asked me if I knew that the country of the United States was bigger than Israel. That's literally what he asked me on my first day. And then the questions became gradually more and more complicated, more and more interesting. And I'm still working on some of the questions that he asked me later that year. But I've never mustered enough courage to repay with my own question. And now that I was preparing for this trip, it occurred to me that there was a great opportunity to repay with a question. So the guiding principle behind this question is that Israelis don't like to be fooled or cheated. So we're always vigilant about not paying too much to some service or stuff like that. So when I went to the courier office in Israel, I was thinking about sending some gift, which in the end I ended up bringing by plane. But anyway, I went to the courier service and they told me that the shipping cost would be determined by the sum of the linear dimensions of the rectangular box. Like the sum of the width, length, and height. And I immediately thought, oh, that sounds suspicious. Could I pack a box into a cheaper box? So my question to Nari and everybody else is whether one can pack a box into a cheaper box. Okay. So many happy birthdays. Happy birthday, many, many happy returns. And I'm sure that Nari will keep making great discoveries. Now let me switch to the physics part. So the physics part is about something that, of course, Nari worked on a lot during the years. So my purpose is to revisit some questions in n=2 quantum field theories, mostly superconformal quantum field theories in 4 dimensions. There are various applications for geometry, integrability, and stuff like that. And also many of the things that I am going to say carry over more or less directly to 2, 2 supersymmetric theories in 2 dimensions. And I'll make some comments about that mostly towards the end. So the plan is to start from some simple review of ideas in conformal field theories that have nothing to do with supersymmetry. So I'll just review some concepts for those of you who are not familiar with that, even though I doubt that there are such people here in the audience. And then I'll make more technical, I'll discuss more technical aspects of n=2. So in conformal field theories, there are the so-called primary operators. These are operators that transform very nicely under a certain class of transformations, which are the conformal transformations. So if, for example, you rescale space and time in a conformally invariant quantum field theory, then these operators are going to rescale very nicely, homogeneously. These are primary operators, so they rescale very nicely with some weight, which we call the conformal weight. Now, in these theories, which have conformal invariance, the physics essentially doesn't care about length scales or dimensions. It cares only about angles in some vague sense. So it's very natural to try to study conformal field theories, not just in flat space, but on more general spaces, which are related to flat space by a conformal factor, omega squared of x, which is taken to be positive definite, no negative definite. So an example for such a conformal factor would be this function, and then the metric on this space is just the stereographic coordinates metric on the sphere. So in some loose sense that I would like to investigate a little bit further, the physics of conformal filters on spheres and in flat space should be closely related. They should be closely related because they are related by a conformal transformation. So one of the main things that I would like to ask is, to what extent is this true? What aspects of this are true? And what are the interesting cases that, in which this is not true? So let's think about the consequences of this idea that flat space and the sphere are conformally equivalent to each other. So primary operators are usually said to transform very nicely under conformal transformations. Or more generally, when you study conformal filters on such conformally flat spaces, such as the sphere, the primary operators on the sphere and the primary operators in flat space would be related by a conformal factor raised to some power. So a consequence of this is that since the expectation values of primary operators in flat space vanish just by dimensional analysis, there is no dimension in flat space to soak up the one-point function, you would conclude that the one-point function on the sphere vanishes. This is something that appears in many papers. It has been used for many, many different arguments over the years. And I would like to discuss to what extent is this really true, that the one-point functions of primary operators on the sphere vanish. So the sphere has a dimensionful parameter, which is the size of the sphere, the radius of the sphere. And so one could, in principle, just by dimensional analysis, write down that the one-point function on the sphere is just the radius of the sphere raised to the appropriate power. So dimensionally, from the point of view of dimensional analysis, this equation is confusing because it might have been non-zero. And one can think about this as saying that the primary operator is mixing with the unit operator. So this in some sense violates our expectations that the sphere and flat space are the same up to a conformal transformation, because now primary operators are not transforming very nicely when you go from flat space to the sphere. They might mix with the unit operator. So the question is, how badly can you violate the expectation that primary operators are more or less the same in flat spaces and on the sphere? So the general principles of quantum filtering allow such violations, but they only allow such violations if they're sufficiently mild. What does it mean that they are mild? They have to be related to contact terms in flat space. Now this is somewhat an abstract criterion, but what it means in practice is that the mixing between primary operators on the sphere is limited, and operators can only mix with other operators if their dimensions differ by even integers. So you can only have even powers of the inverse radius. So there can be the radius to the power -2, -4, -6, and so on. In particular, the mixing with the unit operator that we've discussed here can only happen if delta is an even integer. So the violation of this intuition that correlation functions in flat space and correlation functions on the sphere are the same is limited. The violation is only by even integers, mixing of operators whose dimensions differ by an even integer. And one can trace back this operator mixing to some contact terms. And the standard thing that we would say is that we can tune these contact terms in a convenient fashion. So when we say that correlation functions on the sphere and correlation functions in flat space are the same for primary operators, what we really mean, if we want to be precise, is that there is a renormalization scheme in which the 2-point functions on the sphere are diagonal. So we can choose these contact terms in flat space in such a way that this mixing between operators would not take place. So the 2-point functions on the sphere will be diagonal in dimension, as we expect in flat space. And that in particular also implies that all the 1-point functions of non-trivial operators vanish. So the more precise statement is that there is a scheme, a certain point in the space of renormalization schemes, where this idea would be true. Now, there are some intriguing situations, intriguing and interesting situations where such a scheme does not exist. So when a scheme does not exist, you could say it's an anomaly of some sort. So there are some interesting situations when there is no scheme in which the 2-point functions on the sphere are diagonal in dimension. And I'm going to discuss one such example, which is Seiberg-Witten theory. But let me just talk about the more general aspects of this story first. There is no complete classification of the cases where such a scheme does not exist, but we know of examples where such a scheme does not exist. And it's more or less clear how to go about and perform this classification. It's only very hard. The root of the problem is that to find a point in the space of renormalization schemes where these two-point functions would be diagonal in dimension space, one has to tune various contact terms. But sometimes tuning these contact terms to what you would like or what you would desire breaks some symmetry, which we may view as more sacred. So for example, supersymmetry. So if, say, you want to preserve supersymmetry or some other symmetry, you may not have this point in renormalization scheme space at your disposal. So this point may not be reachable if you want to preserve some other symmetries. And that's the standard situation in which anomalies take place. Another quick reminder that I would like to make is of the concept of exactly marginal operators. Of course, that is something that is familiar to most of you, but I'll just want to set up the notation. So exactly marginal operators are operators of dimension D, and if you add them to the action, the beta functions of the associated coupling constants are vanishing. There could be few of them. There is a manifold of conformal filters, which I'm going to call M. It's going to be a central concept in this talk. So this is the space of all conformal filters which are continuously connected. They're given by deforming some conformal filter by exactly marginal operators. The beta functions vanish, and the dimension of this manifold is some integer. Now, the existence of these exactly marginal operators may appear to be unlikely, because the vanishing of beta functions is not something common, but in fact it appears in experiment, and it has been observed already many decades ago in the Ashkin-Teller model, which is a two-dimensional statistical model. So the existence of exactly marginal operators is commonplace, and they're going to be a central part of this story. Zamolodchikov has found a canonical way, to introduce a metric on the space of conformal filters, the Zamolodchikov metric. His suggestion was simply to take the two-point function between these exactly marginal operators, normalized in this way. So we should think about the space of conformal filters as a manifold with some metric. It's a Riemannian space, a Riemannian manifold. And there is a tangent space, and one can ask questions in geometry about the space of theories. So Zamolodchikov's idea essentially allows us to put geometry in the space of theories, a rigorous sense of geometry. Okay, exactly marginal operators are also commonplace in supersymmetric theories. For example, if you look at Seiberg-Witten theory, which is an SUN gauge theory with 2 and C flavors, hypermultiplets in the fundamental representation, then there is one exactly marginal operator, one complex. And so there is a Riemann surface of such theories, or a curve of such theories. And it would be interesting to compute the Zamolodchikov metric. So the central question that I would like to address in this talk is that Seiberg-Witten theory comes with an exactly marginal operator. And so there is a manifold of such theories. And the central question is, what is the metric on this space? This is a question about Seiberg-Witten theory that wasn't solved in the 90s, but we can solve it now. And this idea of operator mixing on the sphere is going to play a crucial role. So we will have an exact computation of this metric. In fact, one can also define naturally various holomorphic vector bundles over the space of conformal filters. So it's not just the manifold of theories, but one can also talk about all the irrelevant operators at each point, and they form some vector bundle. In the context of supersymmetry, they follow the chiral operators that I'll soon define form a holomorphic vector bundle, and one can ask what's the metric on this space. We will find that the metrics on these holomorphic vector bundles, as well as the metric on the base, are related by interesting recursion relations, which are closely linked to integrable models. So that will be one of the conclusions. Okay, so in n equals 2 superconformal filters, there are these natural operators, which are called the chiral operators. They are annihilated by half of the supercharges, q bar 1 and q bar 2. These operators have a protected dimension, which is related to their global symmetry charge under the U1R symmetry via this formula. So their dimension and R charge are related up to a factor of a half. And these operators, of course, play a huge role in Seiberg-Witten theory. We will refer to the set of such operators as the chiral ring. So as a matter of, to be concrete, what I'm going to study in this talk is the minimal non-holomorphic observable in Seiberg-Witten theory. Seiberg-Witten theory is about the correlation functions of products of these chiral operators, but you're not allowed to insert an anti-chiral operator. So, however, here what I would like to discuss is the minimal non-holomorphic observable in Seiberg-Witten theory, which you can also call an extremal correlator, where you have some number of chiral operators, which are annihilated by half of the supercharges, and one anti-chiral operator, which is annihilated by the other half. So this is a completely non-supersymmetric correlation function. There is no supercharge that leaves the whole correlation function invariant. Now, because these operators carry some U1R charge, this correlation function has a selection rule to it, and it can be non-vanishing only if this is satisfied, only if this equation is satisfied, because then the R charge of the total of the correlation function vanishes. Now, the Zamolodchikov metric is part of this. So the extremal correlators also encompass the Zamolodchikov metric. The Zamolodchikov metric would be the two-point function of O and O bar, where O has dimension 2. So the associated delta is 2. This is the primary operator, which generates the conformal manifold in Seiberg-Witten theory. So a specific example of an extremal correlator is the Zamolodchikov metric correlator. And the higher correlation functions that appear in the chiral ring can be interpreted as giving some metric structure on some holomorphic vector bundles. They also have a nice geometric interpretation. I would like to emphasize that if we knew all the two-point functions of the chiral ring, meaning O and O bar, for all O and all O bar, and if we knew the ring structure, meaning the chiral ring relations, the product rules, then all of those would be fixed. We could collapse all these chiral operators to a single chiral operators by doing the product successively, and then we are left with a two-point function that we assume that if we know, then we've solved this correlation function. And here in some small print, you can see the proof for this statement. So all the extremal correlators are essentially fixed by two-point functions. So all you need to know is the two-point functions and the chiral ring relations. So let's talk about examples. The first example is n=4 theory. This was argued by Lee, Minwaller, Gamani, and Seiberg that in this theory, these extremal correlation functions, which include an arbitrary product of chiral operators and one anti-chiral operator, are exact at tree level. So these are completely trivial in some sense objects that are saturated by tree diagrams. This allowed for extremely interesting and non-trivial checks of the ADS-CFT duality because you could compute some three-point function in weak coupling and compare it to the predictions from supergravity in ADS-5. So there is a famous quote of Nati that this is a theory 7, that we can obtain exact results with approximate methods. And that's a very nice quote in this context. The next example is Seiberg-Witten theory, which is n=2 rather than n=4. Let's talk about SU2 for concreteness with 4 fundamental hypermultiplets. The chiral ring is known. It's just trace of the vector multiplet scalar squared to some arbitrary power. So this is the full set of chiral ring operators, which are annihilated by half of the superspace. Trace phi squared to the power n. And this theory has an exactly marginal coupling. So the gauge coupling is exactly marginal. It doesn't have a beta function. So we have a space of theories, a two real dimensional space of theories. The chiral ring relations are trivial. When you multiply On with Om, the power adds up to n plus m. So these are the product relations. And so the interesting question about Seiberg-Witten theory would be compute the two-point functions On with O bar n. Okay? Those would give us all these interesting metrics on the space of theories and on the space of vector bundles of this chiral ring. So the first one of those, trace phi squared with trace phi squared bar, is just the Zamolodchikov metric on the space of theories. The space of theories is the space of gauge couplings plus theta angles, and this is given by the fundamental domain, which is a well-known fact. Because of duality, the space of theories is given by the fundamental domain, and what we're interested in computing the metric on this space. More generally, if we take n to be bigger than 1, then we have trace phi squared to the power n with trace phi squared bar to the power n. And this gives a metric on some vector bundle. Now there are many perturbative computations of this metric. This is something that was done before I got interested in the subject. People have done perturbative computations of these metrics, for example in this paper. And they found that unlike in n equals 4 or in the Ashkin-Teller model, the metric on this space of theories is not protected. There is an interesting set of perturbative corrections of which people computed the first few terms. So this is explicit computations with Feynman diagrams. And it was known for a long time, therefore, that the metric on the space of Seiberg-Witten theory is not just the metric on the upper half plane of Poincare, it has corrections. And this is just an expansion around weak coupling. So the question is clearly non-trivial. It's not like in n equals 4 that it's tree-level exact. In SUN, one has a similar story, albeit a little bit more complicated, because the chiral ring is parameterized by some vector rather than by some integer, depending on the number of powers inside the brackets and outside the brackets here. The metric is still measured by that specific two-point function, and the metric is still known to have non-trivial corrections. So it's not just the metric on the upper half plane of Poincare. So let me start with the main claim, one of the main claims. So the main claim is that in Seiberg-Witten theory, this idea that one-point functions on the sphere and one-point functions are in flat space are the same is incorrect. There is no renormalization group scheme. There is no scheme in which this is correct. It turns out that the correct result is that the one-point function on the sphere of trace phi squared is actually physical, and it's completely determined in terms of the metric on theory space. So this is the first claim. It's a claim that there exists a certain anomaly in n equals 2 supersymmetric theories, in which there is necessarily mixing between this operator and the unit operator, and we know the coefficient. We've computed the coefficient of this anomaly. It's given by the derivative of the Keller potential on the space of theories. So the one-point function on the sphere in SU2 with 4 hypermultiplets is necessarily non-vanishing. One can even write this anomaly that necessitates this operator mixing in superspace. It's some supersymmetric version of what's called the Panait's anomaly, if you've heard about the Panait's operator. But in any case, this is a clear demonstration that in some theories there is a problem with mapping between flat space and the sphere because there is an anomaly. On the other hand, the one-point function of the sphere can be viewed as the first derivative of the partition function of the sphere because the gauge coupling generates this operator. This is actually slightly non-trivial because if you take a derivative with respect to the gauge coupling, you would expect that you would lower from the action an integrated version of the top component of this supermultiplet. But there is some word identity that allows you to get rid of this top component and replace it by the bottom component, but not integrated, rather at one point. So there is some argument for that here. So the conclusion is that on the one hand, it's the derivative of the partition function, but on the other hand, it's given by the derivative of the Keller potential. And therefore, we have found that the four-sphere partition function must be an exponential of the Keller potential in theory space. So this is an interpretation for the physical meaning of the four-sphere partition function in this theory. It's just an exponential of the metric, of the Keller metric in theory space. This has many consequences for topology and geometry, and some of them are new, even for mathematicians. The first thing is that once you've if you look at this formula, it looks weird because the Keller potential is not actually well defined. It's defined only up to holomorphic and anti-holomorphic functions. So for this formula to make sense, and for this to be a partition function rather than a partition section, one has to demand that the Keller potential is actually well defined. So more precisely, one has to demand that there are no cycles in theory space through which the two Keller form would have flux. Or more mathematically, more precisely, the Hodge bundle has trivial Chern class. This is the Hodge bundle of the space of theories. So what it means is that the space of theories cannot have cycles, essentially, even dimensional cycles. Also, it means that the space of theories cannot be a compact space. So when we have a space of theories connected by some continuous coupling, it cannot be compact because it would violate this condition if it were compact. The same is true also in 2 dimensions, as I mentioned. Many of these ideas are also true in 2 dimensions. But in 2 dimensions, the metric in theory space has another interesting interpretation. It's just the metric on Calabi-Yau spaces, which is the standard Weil-Peterson metric. So we see here that this has no, so the Hodge bundle associated to this has vanishing Chern class. This is a result about algebraic curves that is new to mathematicians, and as far as I understand, they have not found counterexamples. This raises some open questions which are of physical interest. So we see that the space of theories cannot be compact, but it always has finite volume in simple examples. So this space may look, well, this space is non-compact because it can go all the way to infinity. But if you actually study the volume, then it's finite. It raises a natural, so this story raises a natural conjecture that perhaps the space of theories has always finite volume, and we don't know whether this is the case. A related question is that whether the non-compact directions always correspond to weak gauging of some global symmetry. This is true in examples, but we don't know if this is always correct. Another very natural conjecture that arose from these investigations was that the curvature on the space of theories is always non-positive. This seems to be true, at least numerically, or in simple examples, but it has not been proven to be true. It would be of interest, a lot of interest to mathematicians to establish this result. So let's continue studying the Seiberg-Witten theory, or n equals 4 for that matter, with SU2 gauge group. So we're now interested to going beyond the Zamolodchikov metric. We can also compute the 2-point functions on the sphere of trace phi squared to the power m and trace phi squared to the power n. This is non-diagonal in m and n because of these anomalies that induce a mixing between operators of different dimensions. And one can give an explicit expression for that in terms of the four-sphere partition function. This is just a derivative of the four-sphere partition function with respect to tau and tau bar. But because we've already shown that the four-sphere partition function is an exponential of the Kähler potential, one can simplify this formula. This is not yet very interesting because this is just the 2-point function on the sphere. We're ultimately interested in computing these 2-point functions in flat space. This is done by the Gram-Schmidt procedure. The Gram-Schmidt procedure is something that's naturally constructed to eliminate these kind of mixings that these anomalies induce. So the anomalies induce mixings between chiral primary operators, and the Gram-Schmidt procedure by construction can eliminate them successively. So let me give you a quick example. Let's talk about the operators of dimension 1 and 2. So the 1-point function on the sphere is the four-sphere partition function by definition. The 1-point function of the unit operator. Then the 1-point function of trace phi squared is the first derivative, and the 2-point function is the second derivative. The Gram-Schmidt procedure just tells you that you have to take a determinant to remove this mixing, and then you will get flat space results. So the flat space 2-point function, which is the Zamolodchikov metric by definition, is the determinant of this matrix. And this is given by the second derivative of the logarithm of the partition function, and given that this is e to the k, this is exactly the metric. So that's exactly what you would expect. That the 2-point function in flat space is the Zamolodchikov metric, and the four-sphere partition function is therefore the exponential of the Kähler potential. All of this ties nicely with the story about anomalies and mixing with operators. These determinant formulas actually continue. I'll go back to the previous slide in a second. So you can repeat the same procedure with the same Gram-Schmidt procedure for the higher correlation functions, and now therefore you have a closed form formula for the 2-point functions in flat space of trace phi squared to the power n and trace phi squared bar to the power m. So this is a non-trivial non-holomorphic correlation function, which we can now write as a ratio of 2 determinants of the four-sphere partition function. So that's the general structure that you would get. You get some ratios of determinants of four-sphere partition functions. Now, of course, the four-sphere partition function is also known exactly by the work due to the work of Peston on localization, so we can use it to actually extract data. We can use it to extract data about the metric in theory space, compute curvatures. For example, this is the one instant on correction to the Zamolodchikov metric in Seiberg-Witten theory when you expand around weak coupling. So one has all the coefficients, and one can contrast that with perturbative computations that existed previously. And as far as we could see, this proposal of ours checks out. It completely agrees with all the previous results, which are perturbative by nature. So there is a prescription that allows to compute any extremal correlator in n equals 2 theories, and it has some applications that I'll discuss. But first, I would like to make a comment about some relation to integrability. So experts in integrability have found out that ratios of determinants of some function occur naturally in some integrable models of the Toda type. And it turns out that one can actually construct the mapping to an integrable model. So these correlation functions that we've discussed of trace phi squared to the power m with trace phi squared bar to the power m, they obey recursion relations in the parameter m. So the metric on the base space is related by some recursion relation to the metric on these holomorphic vector bundles. So these structures are not completely independent of each other. And it turns out that they obey the Toda equation. So it's exactly the Toda equation with some boundary condition. So it's the open Toda chain with some boundary condition. And in fact, the only thing that distinguishes n equals 4 and n equals 2 with SU2 gauge group is the boundary conditions at the open end of the Toda chain. So one is exact at tree level, the other is extremely non-trivial, and the difference in the language of integrability theory is just the boundary condition, the forcing of the first oscillator in the Toda chain. So that's a very nice story. More generally, we've proven that every n equals 2 theory gives some integrable system for the space of correlation functions of the chiral ring operators. This is something that was proven. The integrable system that you find for n equals 4 is particularly simple, which is consistent with the results of Nati et al. About extremal correlators in n equals 4. You get decoupled Toda chains. But for super QCD, with higher gauge groups, SU3, SU4, we could not completely determine the integrable system except proving that it's integrable. So it's still an open question to try to understand what exact integrable system do you get in general n equals 2 theories. So in SU2, we've identified it as a Toda chain, but in SU3, we have not been able to identify the integrable system as a concrete known model that people have already discussed. However, we've proven that it's integrable. Okay, one can also test some ideas about quantum field theory using these results about non-holomorphic observables, which is kind of nice. These observables have a non-trivial perturbative expansion, so one can test all the ideas about the effectiveness of Padé approximations, Borel resummations. So this is some demonstration of how well the Padé approximation actually works at very high orders in perturbation theory. Here we went up to order 80 in perturbation theory. So this is something that you can read more about or ask me later. So let me just summarize before I continue to discuss a little bit of two-dimensional physics. So the chiral ring of n equals 2 theories are essentially solved in the sense that we can compute these extremal correlation functions, and those allow us various interpretations in terms of the metric on some space, theory space, and so on and so forth. They're always Farnish integrable systems. We've not been able to identify these integrable systems in all cases, so it's still an open question. But it does allow us to test ideas about Borel resummation, Padé approximations. There are also interesting applications for ADS-CFT. These extremal correlators appear very naturally in ADS-CFT. They describe the 3-point couplings between protected operators. And so given these developments, one can now compute the exact extremal correlators, let's say, in the large n limit of Seiberg-Witten theory. So this was applied using these techniques by Rodriguez, Gomez, and Russo, and they found lots of interesting new structures. There are many open questions, including these integrable systems for higher rank gauge groups and various others. I would like to make very few comments about two-dimensional theories because there are slight differences in 2 dimensions compared to what I said about 4 dimensions. In 2 dimensions, there are old results by, for example, these fellas and others, that the space of theories, this conformal manifold, actually factorizes to chiral and twisted chiral Kähler manifolds. So there is a separate Kähler manifold for the chiral exactly marginal operators and a separate Kähler manifold for the twisted chiral exactly marginal operators. And this has been proven in various ways. They gave some specific proof, but there are also proofs using Seiberg's method of promoting coupling constants to fields. So one can also compute these metrics exactly. So one can repeat essentially everything that I've said about 4 dimensions in these 2-dimensional theories, and the metric on these theories is now known exactly. There are 2 ways of putting these theories on the 2 sphere. They are different by some redundant operators, and this is well understood. It again has to do with some one-point function anomalies. The story is essentially the same, and one gets these 2 formulas. So there are 2 sphere compactifications which allow you to compute separately the twisted chiral and chiral Kähler potentials. One novelty is that the chiral ring is not freely generated. So in all the known n equals 2 theories, the chiral ring is freely generated, like you get a trivial chiral ring algebra. In 2 dimensions, because of Coleman's theorem, it cannot be freely generated. One has to have nilpotent elements. In fact, every element has to be nilpotent by Coleman's theorem. So operator mixing, however, still takes place, and one still has the Gram-Schmidt procedure, and one still finds ratios of determinants. And therefore, one still naturally finds solutions to the Tt-star equations and some natural connections to integrability. This has not been explored so far in great detail, but in some simple examples, we have checked that these procedures, these ideas are consistent with previously known solutions of the Tt-star equations. A central puzzle that we were recently interested in with Nari and Hiroshi and Yifan and Jaume is that while there are results in the literature that say that the space of conformal filters factorizes into two Kähler manifolds, there are some exceptions. So for example, if you look at the case-free manifold, then the conformal manifold is a homogeneous space. And this homogeneous space does not admit any Kähler structure. In fact, it doesn't even admit a complex structure that is invariant under this symmetry. So recently we were interested in this apparent contradiction between previously proven theorems about this factorization and some examples like K3 and T4. So what we found is that while K3 is certainly a 2,2 sigma model and these proofs should have worked, it turns out that these proofs have an anomaly that people have overlooked. And so there is some loophole if the R symmetry algebra is actually larger than the 2,2 supersymmetry algebra. And one can prove that this is a necessary and sufficient condition. So this is actually interesting because it shows that this Spurian analysis method that Nari has introduced, where you promote coupling constants to superfields, while it's extremely powerful, there are some very subtle and perhaps esoteric cases where it slightly fails. Because using this method, one would have found the incorrect result for these 2,2 sigma models, but it's clear that this is an anomaly that is associated to these extra R symmetries, and so some corrections need to be made to the method, and we're working on that. So I'm done. So concretely, one idea that would be really interesting to nail down is this question, whether the curvature is always non-positive, the scalar curvature. I don't know how to do it. The bottleneck is that there are instanton corrections and one has to sum them up. And I don't know if there is a convenient way to do it. So at the moment, I think, well, there are extremely good numerical methods of doing it. And numerically, it seems to be correct. But I don't know how to analytically prove that this is correct. I also don't know how to analytically, well, I don't know how to compute the volume. So for example, one canonical question would be, given this moduli space of Seiberg-Witten theories, let's say for SU2, what is the volume of this space? I don't yet know how to answer these questions. Right. So these sigma models are on hyperkähler manifolds. So they have a H2,0 in the Hodge diamond. Sure. This is in one-to-one correspondence, at least at weak coupling, at large volume.
So you have that anomaly if and only if you have hyperkähler target?
That's what we claim. But our claim is a little bit more general because it's in the language of conformal filters. It's not in the language of geometry. So the two claims would overlap when there is a geometric description.
It doesn't have to be hyperkähler. T6 has this anomaly.
Right. It has to have.
Sigma models. That's a sigma model.
Yes.
Yeah. T6 target space. It has the same anomaly.
Right.
It's not hyperkähler. Yeah.
Right. For Calabi-Yau, the condition is hyperkähler. But more generally, the condition is that there is an extended R symmetry. And that captures, we believe, all the cases. T6, T whatever. This seems to be the most general condition one should impose.
Any other questions?
Concerning the first part of the talk about one-point function on a sphere, isn't there a very basic example just from the Weil anomaly, from the trace of the stress tensor and given dimensions?
Right. This example, first, of course, so in some sense, of course, you're right. The trace anomaly is an example of some mismatch between flat space and the sphere. However, that example is different by nature because we're talking about the expectation value of an operator, T mu mu, which does not exist in flat space. It's a redundant operator. It's not an operator. It's not a primary operator in the conformal filter. Here, the things that I've discussed are conceptually different. Sorry. Here, what I've discussed is the. Sorry, I'm losing my way between the slides. Here, what I discussed is the fact that primary operators in flat space can mix with other primary operators due to anomalies. And these mixing coefficients are physical in some cases, but in most cases they can be tuned away. For the redundant operator T mu, the story is different. That it's always given by the A anomaly, and it doesn't exist in flat space. So this is an anomaly that plagues primary operators. So I think it's conceptually different.
Okay, thank you.
Any more questions? If not, let's thank Zohar again.